Okay, now continuing on with what we have regarding homogeneous equations. Now we looked at Newton's law of cooling, and if we cross over to matters of finance, okay, now something you have likely seen from pre-calculus, and we have regarding continuous compounding of interest. And the formula that you see here, A is equal to P times E to the R times T. This is for a one-time deposit, and for the variables present, again, A is going to be the future value, P is the principal or the present value, that is the amount that is put into an investment or account. R you have as the rate of interest, which you would express as a non-percent decimal in the formula, and T is going to be for the amount of time. And looking at crossing over to what we have, say that you have recurring deposits, okay, and where you can have differential equations to be applied, okay. And let's say that you have an account where interest is compounded continuously, and you want to put in a rough estimate on a consistent basis every year. And we have for recurring annual deposits P, where interest is compounded continuously. Okay, now for what we have here, okay, so we have dA over dt, and that's going to be the change in the account balance with respect to the change in time. Okay, we have is equal to the rate of interest R times the amount A plus P, P being the recurring deposit amount. And if we look at solving in terms of the variable A, okay, and we have, again, so here we have in the derivative, okay, A is the dependent variable, T is the independent variable. And if we look at separation of variables, okay, and you have in terms of A, okay, so you have dA, the differential, and on the right hand side we have RA plus P. And if I set things up, okay, where I'm going to have a logarithmic expression, so what I can do is that I can separate the variable expressions by simultaneously dividing the whole equation by RA plus P, as well as multiplying by the differential dt. So we have the terms in A on one side of the equation, and also we have nt on the other. Okay, and upon separating, we can go ahead and integrate. And for what we have in terms of the antiderivative, so we got for just quick items right here, just to sort of step over to the side here. So you have dA over RA plus P. And we looked at integrations. Okay, we had the reciprocal of binomial expressions where we did not yet use substitution, but this is going to be one of the cases where we will. Okay, so we have letting u be equal to RA plus P and expressing, so we have taken the differential on both sides. So u goes to du and differentiating with respect to A. So we have that du is equal to R dA, and expressing the relation in terms of dA. Okay, so you have the reciprocal of R du is equal to dA. And following through and writing in terms of u substitution. Okay, so we've got, okay, so you have du over R in place of dA. What I'll do here, so I have 1 over R times the integral. We have du, okay, and u is in place of RA plus P, and integrating with respect to u, okay. So you got 1 over R, and du over u will have an antiderivative, okay, which would be the natural logarithm. So you have 1 over R times the natural logarithm of the absolute value of u followed by the constant. And looking at back substitution, okay, so we have 1 over r times the natural logarithm of the absolute value of Ra plus P followed by the constant. Okay, and so just going back to what we have here, okay, and so I'm just going to take the antiderivative and I'm just going to have the constant on the right hand side. So we have in establishing, so we have 1 over r times the natural logarithm of the absolute value of Ra plus P. And to the right, okay, so I have is equal to T plus C. And looking at what we have upon multiplying both sides by r. So multiply by r, okay, so r times 1 over r, we go to 1, then we have times the natural logarithm of the absolute value of Ra plus P and we say we have is equal to r times t. And you have r times c, but I'm just going to put this in terms of, let's say, a different variable. Okay, so we have alpha. Okay, so just referencing. So you have that alpha is equal to RC. And this is just in case some of you are wondering, where did this alpha come from? All right, so we got in following through. Okay, so I'm looking at solving in terms of the dependent variable a. So I need to go ahead and take care of the natural logarithm. And so both sides of the equation I can treat as powers to which the natural logarithmic base e is raised. So we have in the follow through. Okay, so I have e to the natural logarithm of the absolute value of Ra plus P. And we have is equal to e to the RT plus A. And I can just go ahead and condense this. Okay, we're going to have, in this case, we can just go ahead and say e to the RT times e to the A. Just kind of mention here, you know, there might be some element of redundancy, but just to restate, it's often easy to overlook, okay, some of the exponential properties that we have stressed in pre-calculus. Okay, so you had the reverse of the product property of exponents. Okay, and so we have on the left-hand side at this stage, okay, so have e to the natural logarithm. So we're going to have the absolute value of Ra plus P and we have is equal to e to the RT times e to the A and a constant raised to a constant, okay, will be yet a constant. Okay, so I'm going to do here, we say the absolute value of Ra plus P is equal to beta times e to the RT, and taking care of what we have, removing the absolute value bars. Okay, so we have Ra plus P. And once you do enough practice, okay, you don't have to worry so much about stressing the signs positive or negatives, because we'll be looking at directly working with just constants. Okay, so you have plus or minus beta, and we'll just put this in terms of yet another constant, okay, whether it's positive or negative. Okay, positive or negative constant, in this case positive or negative beta, we can just have this represented by gamma. Okay, so we have gamma times e to the RT, and looking at isolating the variable a. Okay, right now we're going to take p away from both sides, and so we're going to have Ra, and so I'm just going to have p on the right hand side and out to the front. So we'll just say we have negative p plus gamma times e to the RT, and upon dividing both sides by r, so a is equal to negative p over r plus gamma over r times e to the RT. Okay, and so just looking at what we have here, and so this will be what we have in terms of our formula here. Okay, and another way that we could write this is that we can say that we have A is equal to 1 over R times the quantity of negative P plus gamma times e to the RT. So this will be, either version will be the general formula, okay, for what we have in terms of solving for A whenever you're looking at recurring annual deposits where you have interest to be drawn continuously.